This week's lab is going to be a catch-all of various different experiments. First thing I'm going to do, or have you do, is actually listen to some of the signals that we've been dealing with in the Fourier series. So what we're going to do is, if you take the connector from the speaker on the bench, so I've connected the negative of my BNC to clip to the sleeve, the outside, and I've connected the positive to both the tip and the ring. So the speaker is, the bottom is the volume control, and the rest is the balance between the two channels. Okay, and we hear the tone from the wave. Now the wave I've generated is a 1 kilohertz sine wave. So we're going to adjust the sine wave and have you listen to the different tone. Now this is not one to do in the lab because it'll drive most people crazy, but I'll adjust the frequency up 2 kilohertz and you hear the difference, I hope. 3 kilohertz, 4 kilohertz. You can actually do a little bit of a sound test on yourself. By the way, the signal level over here is only 50 millivolts peak to peak. Pretty small signal. So 7, 8, 9. I've about lost hearing it. You will probably be able to go to 15 kilohertz or so if you'd like. But as you get older, you lose your higher frequency sensitivity, and so 8 or 9 kilohertz is about the limit for me. I'm going to take it back down to 1 kilohertz, which is the middle of the kind of voice band, and change it to some other waves so we can listen to it. So the first thing I'm going to do is change to a triangle wave, and of course we know a triangle wave has more harmonics than a sine wave. So see if you can hear the difference. Hopefully you can hear that difference from the speaker. So there's our triangle, our sine, and square. So you can definitely hear the harmonics that are in the square wave versus the sine wave. Okay, that's just a little exercise showing you, kind of giving you an auditory connection to these waveforms. Now the last wave we're going to look at is actually the noise waveform, which you can select from sine wave to noise. The noise waveform, as you might expect, looks like all different frequencies. Maybe that's not intuitive, but if you zoom in, you will see that the noise waveform doesn't really change as I change the time base. What this means really is that the noise waveform contains all frequencies. Now if you do an auto sweep on here, you can actually see the triggering that it's actually a pseudo noise signal. Meaning that it's generated, but if I zoom out a little bit time-wise, you can see that the signal is independent of the time base. This is what the noise signal sounds like. And that's the characteristic, what we call white noise. We're going to look at this with the spectrum analyzer next, and it'll make maybe make a little more sense, and we'll also be covering noise in chapter 4. So I've connected my signal generator under the noise setting to it's still connected to the scope, and now this is what it looks like in the frequency domain. You'll see that there's quite a bit of frequency content up to about, this is 100 megahertz, 200 megahertz, 300 megahertz. Above 300 megahertz, the noise drops dramatically because that's related to the clocking of the function generator. So I want to look particularly at the low frequencies. So I'm going to change my frequency span, the stop frequency, to now 100 megahertz. With the stop frequency set to 100 megahertz, we can see that the frequency content is relatively flat out to about 10 megahertz. It starts to drop off at 20 megahertz. So now we see the frequency, and this is what we would consider wideband or white noise. The frequency is flat for all frequencies, in this case 0 to 10 megahertz. Now you notice the 0 indicator there on the left. If I take away the noise, then the 0 indicator is still there. So that's not a real signal. So we see the noise. Now I'm going to change my span one more time to set the stop frequency to 50 megahertz, so we can kind of look at that little drop there. And we're going to now use some measurements with the markers. So under your markers, you can see that there are 4 markers available. 1, 2, 3, 4, right? So we'll set the first marker at 10 megahertz. Now there's a variety of settings here. You can set a marker delta to compare between 2, or you can do a span pair. We won't worry about that, but we would like to see what's called the marker table. So go to marker table and turn it on. And I already set up these markers, but I'll show you how to do it. I've got markers set at different frequencies, and we'll have to adjust those. So under marker 1 is selected. I'm going to select normal and then 10 megahertz. 10 megahertz. And so that marker is changed at the bottom to be 10 megahertz. And you can see it's a minus 30 some dBm signal. Go to marker 2 and normal, and we'll set that one at 20 megahertz. Right, so now at the bottom we see 20 megahertz. And then you can see there's a little dip in the frequency. So I'm going to use my my dial to find out where that is. So marker 3, dial it over to that little notch, and somewhere around, looks like to be like 21 1/3 or so megahertz, it dips down. And if you want to do another marker, you can set it up maybe at 50 megahertz, which is the end of the screen. So then we see our data displayed directly on the screen. This is kind of useful because now you've got documentation of the signals that you wanted. So that's our display. If you want to smooth this display out, you can press trace. So I press trace there. I'm going to adjust my level to be the maximum value, and you can see that kind of averages out and smooths out over time. So there we see the noise signal levels if you don't want them to jump all over. Noise being a random based event, it tends to jump. If I press clear right again, I see the noise jumping all around there. For this last section of the lab, we're going to look at what is called the FFT Analyzer, which is actually a part of our scope. So an FFT Analyzer takes the time samples that the scope records, the voltage and time samples, and it creates a frequency spectrum from that information. Now it's very much more limited than the traditional spectrum analyzer, but because it essentially comes for free with software, it's pretty popular among scope manufacturers. The way we access the FFT Analyzer is press the math button, and you'll see that we have actually a number of math functions we can perform: addition, subtraction, multiplication, division even, and then finally FFT. So we're going to select FFT. Now when we select FFT, you'll notice that we now have a second display in purple here. Okay, now it's a little hard to read, but the settings are all at the bottom. The controls that you will use on the FFT is you can use the control on the right to move the frequency 0, if you will. You can move the level up, and you can change the amount of divisions. There's also some advanced ones that we'll look at. We can also go to split screen, which is sometimes more convenient, and then you see the time domain on the top and the frequency domain on the bottom. Still kind of hard to read these values, so I'm going to move this display up by selecting this key and then dialing it down so we can look at this a little more clearly. Now what we see in the FFT information is that the amplitude is 10 dB per division, very similar to what we have on Spectrum Analyzer. The frequency response is 6.25 kilohertz per division. The 0 is shown as the far left display. There is no 0 indicator. Then 6.25 kilohertz, that's one square, so that'd be 6.25, 12.5, and on up. I'm going to change my frequency to 6.25 kilohertz over here by just typing in 6.25 kilohertz, and we see the spectrum come directly up on the first square. Sometimes it's easier to move that all the way over to the right, so that you have because this FFT normally works from the center out. So if I dial this over to where the center frequency is 0, which is the bottom display here, there's 6.25 kilohertz. The sampling is set at 250 kilosamples per second. That's not very important. Mostly the vertical, 10 dB per division, the hertz per division, and then the center frequency. If I change to 12.5 kilohertz, of course, 12.5 K, I see my appearing on the second screen. Now this analyzer works okay for certain cases, at least gives you a basic idea. If I press triangle waves, we of course should see more harmonics. I'm going to go back to my 1 kilohertz signal just so I can display more harmonics. So there's my 1 kilohertz signal. If I go to a triangle wave, I see the harmonics pop up. If I press to a square wave, I'll see even more harmonics. And my Spectrum Analyzer just turned on, so I'll disconnect it. Now what's useful for this is obviously that it's not as accurate as a Spectrum Analyzer. We don't have bandwidth control, but at least we have a representation of the frequency domain, so we could do some basic distortion tests. Alright, so we'd like to look at a couple signals in here. We did the sine, the square wave. Let's look at the pulse signal. So there I go to my pulse. I'm going to change the duty cycle to something like, what is typical we've used before. We'll say 10% duty cycle. So I'll press in 10%. And we can see the sync function playing a role where we go down to 0 every 10th harmonic. A little hard to see all the harmonics in there because of the time sampling. If I change the time base, I can sometimes get a little better view of the harmonics, but you can see it's a very limited kind of spectrum analyzer. So it's okay for lower frequency work and basic applications, but you'll definitely want to use your spectrum analyzer for anything in the RF frequencies. This is also very limited in frequency. Again, if I dial my 0 all the way back to the left-hand side, we can see those harmonics going out 10, 20, 30, 40, 50, 60, 70, way out in frequency. One thing that's kind of interesting using the FFT is to talk a little bit about the time and frequency interactions and what is sometimes called the duality between time and frequency. The fact that something in the time domain can be represented in the frequency domain. We can work in the frequency domain, change back to the time domain. So the signal I want to look at is kind of the opposite of what we're showing now. We're showing a square wave or a pulse waveform and the frequency domain representation, which is a sinc function. The only reason why the sinc function doesn't go negative in here is that this being a power or measurement, there's no negatives, so everything is essentially rectified or squared, and so we see that response. If I come over to the arbitrary waveform generator and select ARB, I can select new types of signal. And the signal I'm going to select is one that we call the sinc function. So over here, press the right-hand button here, and you can select waveform and built-in waveforms. And the ones we're going to look at is called the sinc function. Now we know the sinc function, that is what we use to calculate the frequency content. But now, when I press that, you see that I actually have the sinc function in the time domain, right? So there's our classic sinc function. If I press this button, you can see it a little clearer. Now, what's interesting about this in looking at the frequency domain is that we see that we essentially have a pulse or only one set of frequencies in the frequency domain. So that's pretty fascinating to see that that allows us to look at frequency domain and time domain in this kind of duality between them. So here's a little better look. So the sinc in the time domain produces a pulse in the frequency domain. Now those are individual harmonics in there, but this is the connection between them. So I'm going to switch back over to my pulse signal, and of course there we see the pulse in the time domain and the sinc function in the frequency domain. So that's one of the best examples of showing the connection between the time domain and the frequency domain and how they're interconnected. All right, so experiment a little with the FFT, and that'll be enough, and we'll talk about it in the class.